This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Good morning, good afternoon, and good evening to all. Welcome to the AI for Good webinar that will showcase the results of the ITU focus group on autonomous and assisted driving. Today, we have with us the 3 editors of the focus group deliverables, and we will know more on their achievements very soon. We are all pretty excited by the AI for Good Summit that will be held physically again in Geneva on the 6th and 7th July at the CICG Convention Center. Also, we are hosting a new online edition of the Future Networked Car Symposium, which is co-organized with the UNECE from 13 to 16 March 2023. And I believe on the chat you will have the web page if you are interested in registering. While we get organized actually to participate to these events, I'm honored to introduce the opening remarks to today's webinars from Dr. Bilal Jamoussi, who is the Chief of the Study Group Department of the ITT. We have a short video message.
Distinguished colleagues, panelists, and participants, thank you for joining us at this AI for Good webinar on findings of the ITU focus group on AI for autonomous and assisted driving. As we enter the digital age, emerging technologies percolate into every sector, including mobility. While the vehicle infotainment systems become more elaborate, vehicles have emerged as our third living space after home and office. People now wish to be entertained even while in transit. But how does the driver focus completely on the task and responsibility of driving in this scenario? This has further propelled the adoption of technologies such as artificial intelligence to support the trend for autonomous vehicles that can effectively sense their environment with high precision, make real-time decisions, and operate with little to no human interventions. However, these AI systems are still not widely deployed due to many reasons, including the need to gain public trust. In line with this, the focus group on AI for autonomous and assisted driving was established back in October 2019 to study the behavioral evaluation of AI systems as a driver, and to harmonize the definition of a minimal performance threshold for these AI systems. In other words, explore how AI can function as a responsible driver. The group completed its work with the approval of 3 technical reports that, in a nutshell, describe a protocol that may enhance automated driving safety. Today, we will learn about the outcomes of the focus group, its unique work that will help shape the future regulations to enable autonomous driving. So please join me in welcoming the 3 editors of the technical reports who will elaborate further on the focus group journey towards autonomous driving. I wish you a successful webinar and thank you all for your attention.
Thank you, Dr. Jamousi, for the opening remarks. And that allow me to introduce Mr. Brim Balcombe from Oxbotica, who acted as a focus group chairman in the past 3 years, as well as editor of one of the technical reports of the focus group. Without further ado, Brim, the floor is yours.
Thank you very much, Stefano. Thank you, Bilal. Yeah, a very warm welcome to everybody on the webinar today. Hopefully you may have joined some previous webinars that we've hosted in collaboration with the AI for Good Summit. So it's been a pleasure to work with them for the last 3 years. And today I'll be presenting the technical report 01, but I'd like to introduce you to Ninki and to Jorit, who will be presenting technical report 2 and 3 respectively. Ninki?
Thank you so much. Hello, everyone. My name is Nienke Vellinga. I am a postdoc researcher at the Faculty of Law of the University of Groningen in the Netherlands. With my research, I focus on several legal aspects of automated driving, and I've been very honored to have been chosen the editor of technical report 02 on ethical and legal considerations, and I'm looking forward to sharing our findings with you.
Hello, everybody. My name is Jorit Kuipers. I'm the owner and CTO of RoboTuner and Green Dino, and I will explain more later on in this session.
Super. Thank you very much, Ninki. Thank you, Jorit. So, as I say, I'm going to be presenting technical report 1. I shall bring that up now. Hopefully, my screen share will work successfully. Can everyone see that?
Yes, I can see it. Perfect.
So the findings. So technical report 01 really focused on the technical specification. As Bilal mentioned, there's a bit of history. The focus group was originated at the AI for Good Global Summit in May 2019. It was then approved as a focus group in October 2019. We ran for 2020 to 2022, had around 350 participants from a diverse range of stakeholders, including other standards organizations, companies working on vehicle design, companies working in AVs, a lot of researchers focusing on ethics, and Ninki will cover some of that work as well. So a really diverse mix of participants, all focused on the technology aspects of automated driving. And then finally, the output of our focus group was passed through to our parent study group for a proposal to create a new ITU recommendation. And that was successful on October at the end of last year. So you can follow this work through our parent study group now. I just wanted to focus on the question here, how safe is safe enough? Gets mentioned a lot. And just split that into 2 parts, authorization and monitoring, where I tend to think of authorization as being the tests that are required before the software is allowed on the road, which enables the public to predict the vehicle's behavior. You know, it should be as similar to a human driver as possible. The part that we then focus on in the focus group activity was on the monitoring side, so explainability. So it's not the control of what the vehicle does, but it's being able to explain what the vehicle did after it happened. And in the regulatory frameworks we're seeing coming from the UNECE and from the EU, this sort of like balance between authorization and in-use monitoring will form part of that regulatory framework. Explainability, as Bilal mentioned, we're focusing on the behavioural evaluation of the AI. So how is the vehicle actually behaving in the real world? You know? That means we're making an in-use assessment, and our activity is really focused on the field monitoring of assisted and automated vehicles. So that's the continual validation of the safety performance. To frame our activities very early on in the program, we came up with a motivating safety case, which was called the Molly problem. We said a young girl called Molly is crossing the road alone, is hit by an unoccupied self-driving vehicle, and there are no eyewitnesses. How can the AD software explain what happened? The AD software is the only witness. So in the context of explainability, there were three main inputs, which were the situational awareness, hazard awareness, and then the mitigating action that the software took. And that would lead then to the outcome, which was, did the behavior actually endanger the public or any property? So the AD behavior explainability is on the left-hand side, and on the right-hand side, you have the behavioral assessment. With the Molly problem, we conducted a survey, had over 450 responses, looking at what type of data elements would help with explainability. So you can see here the public's responses were the time, location, and speed were all things that were fundamental to explainability. You must know where you were, at what time, and at what speed you were doing when the collision occurred. Additionally, in terms of hazard awareness, when the collision risk was identified, if Molly was detected and when Molly was detected, and then if Molly was detected as a human and when she was detected as a human. So it's kind of like an object detection and then an object classification requirement for explainability. And then when almost describes, okay, what the perceived level of risk has reached a certain level. So that became really important as well. And then that was followed by whether, when, and what mitigating action should be taken. And as you can see, for all of these responses, there's an overwhelming majority, over 95% for every single case. So we really took that through and started to look at, okay, well, what data do we need and how would we communicate and share that data for making this behavioral assessment? So in terms of the technical report one scope, we focused on the box on the left-hand side, so the sort of world model representation that can be used to capture information about situational awareness, hazard awareness, and the mitigating action. The arrow in the middle, which is the communication protocol. So how do we share that world model information for the purposes of making a safety assessment? And then the outcome element was out of scope for the work. So that will be future work that will look at the metrics and the thresholds specifically to assess the safe behavior. But it's important that we have the correct raw data in order to make that safety assessment. So in terms of the technical report one and what we've done in terms of the proposed spec that's gone for the ITU recommendation, you can see on the very left-hand side, we have the physical world entering into the automated driving system through sensors, an internal digital world model representation used by the ADS system, which includes the vehicle dynamics, localization, object perception. And then the bit on the right-hand side, then you have the safety assessment system. And the bit in the middle, the blue bit in the middle, is the bit that we focused on for the focus group output. And that's made up of a standardized world model representation and then a standardized communication protocol. I'll focus initially on the world model representation. So for the world model, it's a digital representation of the spatial and temporal dimensions, enables you to understand where the vehicle is relative to the infrastructure, relative to other road users. And it enables you to then extract the resultant vehicle behavior. The world model representation is the foundation to vehicle behavior. The focus group activity defined a common format in how we should share that world model information for the purposes of safety assessment. We've aligned the output with the world model representation used in a common data dictionary defined by ETSI. So it uses the same data frames and data elements, and that will ensure future compatibility with cooperative, connected, and automated mobility solutions. So not just focusing on automated only, but that real future that the cities around the world are looking for, which is cooperative and connected. And so particularly looking at cooperative awareness, vulnerable road user awareness, and collective perception. The idea being that if we have digital systems that are on our roads, they all have the same representation and are able to communicate with each other using that world model representation. So if I see an object, you're able to see the same object, and we're able to agree where that object is located. Within our focus group activity, we define a minimum set of the data frames and data elements that capture the following information. So time, the location to a world coordinate system, vehicle identification, so the VIN number that would normally be on a vehicle coordinate system, for the vehicle frame, so which is really important, the type of vehicle, types of other road users, and then specifically ego vehicle data and other road user data. I'll expand on those a little bit more. So with the ego vehicle data, that's about the vehicle with the autonomous driving system. We've aligned particularly with the cooperative awareness messages from ETSI. So that will give us information about the vehicle's heading, the vehicle's speed, its driving direction, the accelerations in 3 axes, the vehicle dimensions, so its size, the curvature that the vehicle's following, its yaw rate, steering wheel angle, lane position. So critical information about where that vehicle's located in the world and how that vehicle's behaving. For other road user data, we're aligned with the collective perception message, which enables us to then say for any object that's been detected, it has a unique ID, it has the time when that object was detected, it has an XYZ coordinate reference to the vehicle, XYZ velocity, XYZ acceleration, roll pitch yaw, which is angle, speed, and accelerations across those 3 axes, the object's dimensions, its reference point, the object's age, the object confidence, and the classification. So basically, I can see a bus in this location, I saw it at this time, and this is the size of the bus that I'm seeing, and then the confidence at which I'm seeing that, which is really important when you evaluate risk. The output, therefore, of the world model stage is a common representation for that world model. What we want to be clear on, though, is that doesn't prevent the AD companies from using their own representation internally within their systems. This is purely a mechanism to share externally that world model view. The second stage that we worked on was the communication protocol. So that's essential now to actually take the data, the world model, and then share that in a standardized manner so that other pieces of software can then receive that data. What we were looking for was a protocol that enabled a very flexible architecture, depending on how future domestic and international regulations were written. So it enables the data to be shared and then to be consumed on the same operating system as the AD software, on the same compute hardware. It can be consumed on the same vehicle, across a vehicle network, but on different compute hardware, or even transmitted wirelessly to the edge and processed at the network edge, or then onwards into a centralized public or private cloud data center. So that the single protocol that we've chosen enables all of those different modes of operation, which is quite rare for a protocol to be so flexible. The protocol that we've selected is Eclipse Zeno. Zeno is a communication middleware. It's used for communication over Ethernet, over time-sensitive networking, Wi-Fi, 5G, 4G networks, all of which are commonly used within different CCAM solutions. Zeno enables us to the world model data to be published by the AD software and then to be subscribed to by the AD safety assessment system. And again, that safety assessment system can live anywhere, on the vehicle, at the edge, or in the cloud. It also enables the AD safety system to query the world model data on those distributed sources. So no matter where that information is located, the AD safety system can make a request. It will trigger a local computation, and then effectively we would have more efficient data transmission. So it's an incredibly flexible protocol that we've selected. For those that are more technically minded when it comes to programming, this is just an example format where we've shown a data frame for the vehicle indicator section, which shows how we would use the vehicle ID, its geometry, its length, to actually create all of the information about the vehicle itself. And then a querying scheme, which allows us to look for, say, any vehicle of a particular size or any vehicle that's followed, a particular path, which might be useful when you're analyzing a collision that's occurred in a certain location. Yeah, so there's some just examples there, and they're included within the technical report. The output of the communication protocol says is a JSON Bison encoding that will be then transmitted over the Eclipse Zeno standard. Again, it's similar to the comment I made before. The use of Zeno for communicating this data does not prevent the use of alternative communication protocols within the AD software. This is, again, just a mechanism to share data externally for the purposes of AD safety assessment. I'd just like to draw your final attention to the work that's being done with the UNECE. So we've been aligned with their activities throughout the last 3 years. And most recently, I would say our approach aligns closely with their new assessment and test method work from the VMAD group within GRVA, within WP29. And that's really focusing on in-service monitoring and reporting, where you need safety confirmation, effectively about the system itself before it was introduced on the market, scenario generation, which is capturing new events in the real world that you want to make sure that the software will be safe for in the future, and then safety recommendations. So key information about accidents or incidents, and that goes to the level of near-miss events. This explainability framework that we've come up with and that is now going through the standardization process with study group 16 provides a really useful foundation for achieving the aims of the work of UNECE. So with that, I'd like to say thank you very much. I think we'll continue with the presentations and then ask questions towards the end. So I'd like to hand over now to Ninky.
Thank you so much, Bryn. I'll just share my screen. Can you let me know if you can see the screen at the moment?
Yep, that's perfect.
Excellent, very good. So I'll be discussing the findings of technical report 02 on the ethical and legal considerations of continual monitoring. Now, as you can tell from this slide, we have had about 6 contributors from all different disciplines and backgrounds, leading to very interesting discussions. It needs to be said, though, that the report was published in December 2021, so a little over a year ago, which means that like the latest developments of the past year have not been included in the report. And one of those developments I'll highlight later on. So for this report, we took the Molly problem as the starting point again. But here in the survey, we focused on what the participants' normative and empirical expectations are in relation to the post-collision behavior of the self-driving vehicle. What should it do after the collision occurs? And what we got from the outcomes was that participants attached a significant value to what the automated vehicle would do after the collision. And that there were tons of expectations regarding, for instance, calling the police or stopping at the scene of the accident. So what we saw was that people wanted the self-driving vehicle to stop at the collision scene, but they also found that it should stop at the scene of the accident. In addition to that, they felt that the vehicle should inform the police about the accident and also record the accident. Now, we've tried to take those expectations and look at them from an ethical and legal perspective. What is the ethical and legal backdrop against all of this? And when it comes to the ethical framework, we've taken into consideration the work by the German Data Ethics Commission and the European Commission's independent expert group on ethics for connected and automated vehicles. Now, it's of course far too many findings to discuss with you at length, but there are 3 key considerations that I want to explore a bit more with you. What we did is we took a number of the recommendations by the independent expert group from the European Commission and applied them to the Molly problem to explore what exactly from an ethical perspective should have been done post-collision in the Molly scenario. And 3 of those key considerations, one of those is to reduce harm. Now, of course, it's post-collision, so harm has already been done, but you could prevent future harm by collecting data on this specific accident with Molly and to investigate whether there has been something that could have been altered in the vehicle's design or infrastructure design to have prevented this accident. And with that information, you might be able to reduce future harm. So in that sense, reducing harm and the need to collect data can go hand in hand. Of course, the flip side to collecting data is that we also want to have data protection to some sort of degree, especially when it comes to sensitive data. So these two interests will have to be balanced in some way. Of course, we already have some legal tools for that. For those of you who are EU-based, the General Data Protection Regulation will be familiar, General Safety Regulation for vehicles as well. One of the things when it comes to data protection that you could do is also inform the people that are involved in the use of this vehicle, what is happening with their data, for instance. Then one of the final considerations that I'll discuss here with you is the fair and effective mechanisms for compensation. It became very clear from the findings of both ethics groups that there should be some mechanism for compensation of damage that has been done by an automated vehicle. Now, this can be existing mechanisms, but you might also want to explore new frameworks for liability or for insurance, for instance. And that is something, especially the liability part, that I'll be talking about a bit later, but first a bit on the legal framework for the sort of post-collision behavior. We have Article 31 of the Vienna Convention on Road Traffic from 1968. You're probably familiar with that. And in there, we already see obligations for the driver that sort of match the expectations from our participants in the survey when it comes to the behavior, the post-collision behavior of the self-driving vehicle. So under the Vienna Convention, the driver has to stop at the scene of an accident. And in case a person has been injured or killed, he will also have to notify the police. And on top of that, he will have to prevent any changes in the condition of the site of the accident. So in a way, you could say that he has to preserve the site as it is, so that data can be collected from that in order to do investigation work on it. So here you already see those expectations from the MOLI problem well reflected. However, this is a matter of obligations for the driver, and the legal framework at the moment does not provide any legal obligations for the self-driving vehicle just yet. Now, taking the expectations and looking at matters of civil liability, so that's the liability where some damage occurs and someone needs to pay for those damages, compensation is being claimed. We've looked at two different jurisdictions, namely the US and the EU. Now, to start with the US, I should point out that the US has no federal legal framework on product liability. Every state can decide on their own product liability rules. So we couldn't, of course, describe the liability framework of all those states. So we went with one of the most dominant theories in product liability law, strict liability. Strict liability means that there's liability regardless of fault or intent, for instance. And under this strict liability theory, as a manufacturer, you are liable for damage caused by your defective and unreasonably dangerous product. But when is a product defective or unreasonably dangerous? Before I answer this question, I should point out that the product can be a self-driving car. So then the question is, when is a self-driving car defective and unreasonably dangerous? And in US legislation, you see that there are two tests that pop out, the risk utility test and the consumer expectation test. Now, the risk utility test, as the name already sort of gives away, weighs the risks of a product against the benefits of a product. When the benefits outweigh the risk, then it's not defective, the product. When the risks outweigh the benefits, then it's deemed defective and unreasonably dangerous. The consumer expectation test, however, looks at the expectations of a consumer. So this is where you'll see the link with the MOLI problem and the expectations that we saw there. So the consumer expectation test determines whether a product is defective by looking at whether the design of the product makes it dangerous in a way that your ordinary consumer would not expect. And this is a test that has a sort of very similar, well, almost family member, I would say, in EU product liability law. So in the EU, we have the EU Product Liability Directive that makes sure that product liability is harmonized throughout the EU. All member states have There is one thing they can opt out of, but other than that, it's harmonized. Also based on strict liability, so again, no fault is required. And a producer is, or a manufacturer is held liable for damage caused by a defect in his product. Here, of course, again, the question, when is a product defective? Self-driving vehicle can be classified as a product. When is it defective? In this case, the formulation of the legislator has been when a product does not provide the safety which a person is entitled to expect. So here again, we have the importance of expectations regarding the behavior of the self-driving vehicle, both post-collision, in case there's a matter of damage control, for instance, when it comes to alarming emergency services, and pre-collision as well. The expectation of a person, as it's phrased here in the Product Liability Directive, it's not an individual person, it's not my personal expectation, but it's the expectation of the general public. Now, how to assess such an expectation? That's quite difficult, especially when it comes to new technologies. But you take into account all circumstances. So you can think of how a product is marketed, how it's named, what the instructions are, whether there are any warnings, but also whether, for instance, when it comes to a self-driving car, there are specific traffic rules that it has to comply with. For instance, that the self-driving car has to stop at a red traffic light. If it doesn't do that, then it's safe to say that it didn't meet the safety expectations of the general public. So then it will probably be deemed defective. Now, one of the new developments that we haven't been able to incorporate in the report because it's already been published is the European Commission's proposal to revise the Product Liability Directive. They issued this proposal in September 2022, and there are some questions that we've raised in our report that are at least partially answered by the proposal the way it stands at the moment. So that is something interesting if this is something that you're interested in to explore a bit further. That being said, I invite you to read the report, and in case you have any questions now or later on, please don't hesitate to drop us a line. Thank you.
Perfect. Thank you very much, Nikki. Really appreciate that. And then moving swiftly ahead, Jorrit, if you could give the summary for technical report 3, that would be great. And then we'll open up the floor for discussion afterwards. Thank you.
Okay, thank you very much, Bryn. I'm going to present the outcome of our technical report 3, but I didn't do it alone. I had 2 fellow writers, Niels de Boer and James Long, and I also will present their demonstrator. And for us, we saw it as our goal to describe the setups of the demonstrator, because the demonstrators are still in progress and still waiting on results. But the reports, the description should give a good insight in how to set up the monitoring and assessment of the driving behavior of self-driving vehicles. So that was our goal. We have 3 demonstrators, 3 practical demonstrators. The first one I will present is the Smart Mobility Living Lab in London, the United Kingdom, Citroën in Singapore, and Columbus, our own project in the Netherlands. And to focus on the MOLLI problem, we saw especially a possibility for the metrics to focus on the mitigating action. What does the software do to mitigate the risk? And I think that that's a really hard one to bring in the software. And this is described in our demonstrators, how we think we will do it. So first, I will give some insight in the Smart Mobility Living Lab in London, the setup. There are 2 areas in London that those areas are equipped with lamp columns with monitoring for monitoring, and sensors are installed on those columns around the routes. The Queen Elizabeth Olympic Park route is for earlier testing with lower complexity of the traffic conditions. And the other route has more intense traffic situations, and a lot of poles are installed for observing the traffic. Here we see what happens. The events are analyzed and logged. All details of the behavior of the different participants in the traffic are logged and analyzed and objectivated. Then, based on this information, this real traffic, natural traffic scenarios, the scenarios are generated and reconstructed and objectivated. And in open scenario, they are rebuilt, and also the scenario generation and objectivation of risk is then later on done with, I believe, ASAM simulation software. C-Tran has another setup. They have their own area where they can test, but they also test on road, but not with autonomous driving. They do it with shadow driving. But they focus really on the risk evaluation methodology. And they used 3 different environments for it. The first one is MathWorks for the driving scenario design, the AV simulation with Apollo, and they also had an in-vehicle demonstrator that runs on the road, but a human driver was driving it. Here we see the steps in the driving risk evaluation, the methodology, and scenarios are constructed and interaction is defined. And based on this interaction, there is a certain level of risk applied to the situation. And that we see in the second step that there is a level of risk applied. And then it's weighted for the situation, and also there is looked to combined interaction. So not only the risk of the eco vehicle, but also the risk combined with the other traffic along the scenario. So it's tested in 3 environments. I think the interesting environment is on the road. Here a human driver drove the vehicle, but the assessment software was running as well. And the environment was objectivated, but also the risk levels. And we see some calculations for the total risk, but also is calculated how much time the eco vehicle spent in those risky zones. All you can find in detail in the technical report. So our own project is the Columbus project. Columbus is the connected level 5 unmanned buses. And this project focuses on the enhancing of the capacity of public transport of people. We try to do it by lowering the cost per kilometer per person. And we think we can speed it up by an open source autopilot and an open source auto examiner. So that's what we are developing and testing. And we do it for 3 types of buses, the large macro buses, the microbus, it's the little vehicle you see, and also the taxi buses, the mini buses. Those projects are executed in the Netherlands. We have 2 regions where we are active. In the north of the Netherlands is the province of Groningen, and in the west of the Netherlands is the metropole region Rotterdam-The Hague. And we execute the project in 3 phases. We start on bus depots where we drive at low speed and see if the equipment, the autopilot kit, the sensors are stable. But we also drive at higher speed, but then we use the shadow driving methodology. Also C-Tran applies, where a human bus driver is driving his normal route, and the autopilot is also running in the bus, but it's not connected to the vehicle. And so we can also assess not only the autopilot at higher speeds, but also measure the performance of the bus driver and then use it as a reference for the performance of the autopilot. So for the safety metrics, we looked at the national driving procedures used for human drivers. And those are legal metrics. They are in the law embedded, and they are applicable for the driving schools, the examiners, but also the drivers, the police. Everybody has to follow these legal metrics. And it's focused on to have a uniform methodology for risk mitigation. And this was one of the important points of the Molly problem inventory, that the self-driving vehicles should be able to explain how it mitigate the risks that were observed in the environment. And we look at the way human drivers do it, and the human driving performance is then used as the reference for the automated vehicle and how to assess it. We use the safety state framework developed by my company Green Dino. It's a validated risk metric for human drivers, and based on those national driving procedures. We already have more than performances of more than 300,000 drivers in the Netherlands. And we also looked at their performance after getting their license and the involvement in accidents on the road. And we proved that there are valid metrics that people who have more dangerous behavior in the driving simulation environment, they also are more likely to have to be involved in accidents on the road. And we, for example, focus on the safety score of the driver, and it's constructed with different types of behavior on the road, like ignoring the traffic rules, inappropriate distance, inappropriate speed, etc. We will see a more exhausted report with all kinds of driving procedures. And the interesting thing is that we see correlations in those factors, like a safe speed for going to the right, turning right. It also correlates with viewing behavior. This is for human drivers, but also, for example, not using the indicators, and that cumulates to a safety score for the driver. Let's see. Yeah. So here we have a movie where we incorporated this metrics in our driving simulator. So this is a training simulator for bus drivers, and a human driver is driving the simulator. I'm going to do it myself in this video. We have a connected system that gives an overview of the situation. And here I will activate the risk calculation. Interesting is that we look in time in front, so we have the possibility to look ahead in time and calculate the risk that will come, and we see it in a pink vehicle. That's if the vehicle is going to drive, the pink vehicle let us know where it will be in 3 seconds ahead of us. So here you can see that there are risks visible. I'm now turning to the right, do it at a low speed. And we didn't see scores at the moment, so I will activate the scores. We're nearly hitting a vehicle. So I activate the risk, and we see it in the front screen at the top for ourselves, but also the other vehicles have risk values. Now, when I'm standing still, the risk value for myself is 0 because I'm not adding risk to the situation. And when I'm going to drive, this risk is higher. But I can see it back, so I will stop now the vehicle and look at the monitoring system. And here we see the red areas with risk values. And I will go back in time to one of those areas, and there we can see in detail what happened and what we did to mitigate the risk. In this case is to drive at a very low speed in this dangerous situation. So I went back in the timeline. I can go around the vehicle and see what happens there. So because of the little speed I had, the risk value, there was some risk, but it was not a very dangerous situation. So hopefully this gives an insight in the setup of our demonstrators. And again, I also want to thank Niels and James for putting their demonstrators into this report. Thank you very much.
Excellent. Thank you very much, Jorrit. Thank you, Ninky, for the great presentations. And again, thanks for taking the editor's role on each of those technical reports. I think, Jorrit, just looking at the visualizations that you created at the end, obviously they're spatial representations of where the vehicle is in an environment and where the other objects are around. And that's what we've been trying to do with the technical report, is create a common way of that data being captured from any automated driving system. So to enable regulators or approvers of vehicles to be able to effectively simply plug into a vehicle, get access to that data in a standardized format, which means that all of the tools that they're developing, like the ones that you've just shown, are compatible with this standard. At the moment, every autonomous driving company has their own way of representing data, have their own private method of communicating data, and that makes it very difficult for regulators, approvers, or safety analysts, collision investigation to actually access the data in a standardized way. And that's really been the focus of our activity.
Yeah,
I think, yeah.
It's very important, I think, because if we are not aware of what the vehicle does and think, you can imagine 100 different types of self-driving vehicles are running in your city, and one hits Molly, but no one can explain how they examine the environment or see how they determine hazards. Then all have to go from off the road. So I think it's very important to have this common approach. We were not able yet to incorporate it in the software, but we will. So we will rebuild this open source autopilot and assessment software, and we will use these recommendations and try to make a more common approach in it.
Perfect. Ninky, back to the work that you did. I know we had a number of really interesting conversations around the ethics side. I know part of the report looked at the trolley problem and how that trolley problem, traditional trolley problem that gets referenced a lot with automated driving. But there was a statistical significance in the change of behavior in that report that was done. So basically, depending on the post-collision response, people would change whether they drove towards 5 people or drove towards 1 person. And that was really interesting to see, because it's quite rare to see that level of change in people's behavior from an ethical thing, especially if it's happening post-response. So it's more like, do you want to be involved in an illegal hit and run? And the overwhelming reaction that we had from the public was no. do not want to be involved in a hit and run.
Exactly. It was very interesting to see indeed how post-collision behavior changes pre-collision choices in essence. And I think tapping onto what Jorrit just told us about the standardization, I just wanted to make a remark that that's also very important from a legal perspective to have solid, accessible data in order to establish what went wrong, who was at fault, especially in criminal proceedings. That can be very valuable data also for insurance companies, you name it. So all of this work is hopefully building towards that as well.
Yeah, and I think one of the interesting things, so it was the focus group is focused on autonomous and assisted driving, and we don't often talk a lot about the assisted driving. But basically for assisted driving, the principle is very similar. There are always sensors that are located on the vehicle. The sensors are perceiving the environment. They're creating an object model at some level of resolution, so a world model representation. And therefore, the work that Jorrit was showing about the sort of open loop driving, where you have the system running in the background, in theory in future could be used to assess human drivers. So if we want to look at things like close passing of vehicles to cyclists, the autonomous driving system should do that naturally because it needs all of that data. But in the future, the same types of assessments that we're looking, the same types of communication for the data could be used to make that assessment for human drivers as well.
Yeah, I think what is also interesting is that our background is training of human drivers, and we saw from pilots for planes that because of the autopilot, their skills eroded. So if you have a monitoring system on the road for driving behavior and driving skills, we also can measure the erosion of skills because they are not getting this experience anymore. So it also gives opportunities, for example, for driving schools. They think autonomous driving is a danger, a threat to their business. But I think that, for example, for training, more training is needed when automated cars are taking over driving.
Yeah, and I think it's a fascinating topic. I've had discussions a number of times in the industry about automated driving, but also that ability for you to use the same type of system as a constant coach for a human driver. So something that's in there and it's assistive and it's actually helping you become a better driver. So there's an interesting synergy between human and AI as we move forward. So I think that was an interesting area to explore. Ninky, any other standouts that from the report and some of the contributions? You mentioned the work we looked at with the German Data and Ethics Committee. I remember there was a pyramid of risk that was attached. And
yes, exactly. The more risk is involved, the more safety measures you will have to take to counter that. So you get this pyramid. The higher you go, the more risk, and the narrower it gets at the top. Those are the systems that you want to have banned. Those are too dangerous to drive on the road or to engage with public in general. And you can place a sort of safety measures pyramid next to it, but upside down. The more dangerous something gets, the more safety expectations you will have regarding any safeguards to make sure that you use it properly and that it doesn't cause harm. And it's something that at the moment you see quite clearly as well in the proposal for an AI Act at the EU level, where there's also this sort of risk-based regulation. The more risk, the more safeguards, the more obligations you have as a developer, for instance, to make sure that things are safe. So that's really interesting to see there as well, as it also correlates with sort of the safety expectations that we have when it comes to assessing liability. The more dangerous something is, the more we expect that something is being done to counter those risks. Also in the risk utility analysis used in the US, you will see that different designs will be contemplated on. Is there a different design possible for this dangerous product to make the risk not as big, to mitigate risks, that sort of thing. So that's something that comes through in all these aspects.
Yeah, and I think what was interesting is that the Data and Ethics Commission's work was a horizontal framework. So it was just looking at AI applications, and that could be anything from a Netflix recommendation engine, which kind of sat down at the low risk doesn't need to be monitored, all the way to autonomous weapon systems, which I remember being at the top, which would be explicitly banned. And then sitting just below that, I think at level 4, were systems that had a potential to cause serious harm. And if you think about an autonomous vehicle driving on the road, then it has a very high potential to cause harm. And therefore, what was required of those systems was not only approval for them to be sold, but then the continual monitoring of those systems once they were in the environment.
Yes,
and again, that really strongly comes back to our explainability work that we were doing in the focus group and the potential use for the world model and the communication framework that we've come up with. Joris, on your side, anything else that stood out? I know we had some wide-ranging discussions when we looked at how would we take this protocol and start to use it in a real-world environment. And you've captured some of those environments. What do you think the next steps are, to actually embedding this protocol now within those test environments and gathering some of that data?
Yeah, I think that what is very important is the cooperation with the national authorities like the vehicle authority or the driver exam authority, because we can have those tests running, but if they don't incorporate it in their permission methodology, and if they don't get the experience with it, then it will slow down the use of automated vehicles enormously. Like, for example, in the Netherlands, the exam authorities just started to look at this topic, and they have to start from scratch. So I think the working together between the business companies, but also the national authorities is very important in this.
Yeah, and I think that's why when we first started to look at that, we were looking at solutions specifically focused on automated vehicles, and it became very clear that actually cities and the way cities want to move is towards cooperative, connected, automated mobility. And if they really want to change the ways their cities move, the way they can move people around the cities, that's the focus, this CCAM focus. And so we started to look very early on with a liaison that we established with ETSI, specifically about, well, when we're talking about collective perception systems and cooperative awareness systems, how are those vehicles sharing information? So these could be human-driven vehicles, but they're sharing information around what you can see, traffic light status, or what you can see around a corner that's not actually visible. And that type of information was already being shared. There was already some movement towards that and support, obviously, from governments and also from manufacturers in developing those standards. And it made sense to align with those standards for our activity, so that the world model representation that everyone uses will eventually be harmonized. And I think that made a lot of sense when it came to regulation.
I agree.
Super. Any final comments? Again, from my side, I'd just like to say thanks to all of the 350 participants that we had. Thanks again to yourselves and all of the contributors to those technical reports. And then any final words from yourself before we move over to the neural network, the AI for Good neural network?
Yeah, I also want to thank you very much for all the effort you spent to organize all of this and making this possible. So I think also, Nienke, that is your opinion.
Yes, I'll join you in thanking Bryn for leading our focus group. It's been a very interesting experience. I've learned a lot from a lot of people from different disciplines, like Jorrit, for instance, and yourself, Bryn. So I hope to see this work continued in the future, in some shape or form. Yeah, so in that regard, the work is continuing. The focus group itself has ended. That focus group period has ended. Our parent study group 16, has now taken that forward as an ITU recommendation. And so there can be contributions into that ITU recommendation as it becomes an ITU recommendation is effectively a full international standard. So the work is now continuing. That was supported by the UK government in October. And yeah, very, very happy for people to get involved with that, start using the protocol that we've created, and yeah, bring it into the real world.
And that's hopefully what we're doing here at Oxbotica, which is where I'm working now, which is an AV company based in the UK. So looking forward to continuing the collaborations that we've established and actually seeing the real world benefit come to everybody. Stefano, any final comments from yourself?
Hello, okay, here. No final comments. It was very interesting, this webinar, and I hope this was useful for the delegates and the experts that might be interested in continuing this work or contributing to this work into the ITU to make it happen. And that was one of my questions, was what would be the next step for this work to become influential. And I think you kind of answered with this last statement.
Yeah, and I think the next step for us, is, yes, we have that ITU standards, so that will start to look at the world model representation, data communication. The next step is to then deploy that in vehicles, start capturing real world data, and then start looking at the metrics and the thresholds that will be then attached to that data. So things like the passing distance to cyclists at certain speeds become a metric, the actual distance and the speed, they become some of the thresholds. So it's really important we have the foundation now to start building the evidence base for what are the most valuable metrics and thresholds that can be used to establish safety on the road. And that's something completely unique. And as we said, it can be applied to autonomous and assisted vehicles. So I have really positive expectations for the impact that this future standard, once approved, can have in road safety.
Very good. So I just thank you and the other editors for being with us today. And I think everyone will join the neural network for Q&A if there is any in the chat and networking.
And especially our thanks to the ITU for originally hosting the AI for Good Global Summit, where this initiative was kicked off, for being amazing as the Secretariat for the whole focus group period for the last 3 years. So thanks, Stefano and the team. It's been a real pleasure to work with you. So thank you very much, everybody.
Thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.
you.